Okay, this is problem number 7 from chapter 9. Probably one of the more challenging problems that we've had the opportunity to work with here, so I want to try to do my best to explain what's going on. Here we have a rocket ship that's moving through open space, and it's burning fuel, it's accelerating and so forth, but at some later point in time it's just moving through space and it's not burning any more fuel. So let's go ahead and give ourselves a rocket moving through space, and according to the problem here, they said that the rocket was moving with a speed of about 115 meters per second. I'm going to go ahead and put that down here. That's its velocity. And it's got a mass of 3180 kilograms. So this would represent its original momentum, would be that vector. I'm going to go ahead and just call that P sub I, since that vector would represent the initial momentum of the system. Now, what they told us is that it's going to burn some gas so that it can actually move off in a different direction. And they told us that they wanted it to move off at an angle of 35 degrees from its original direction. Now, to do that, it says what it's going to do is it's going to burn some fuel. Now, that fuel is already inside that rocket. I'm going to go ahead and show that fuel inside that rocket before it even discharges. I'm going to think of it as a separate body here, and instead of me considering the entire mass being 3180 kilograms, what I'm going to do is I'm going to say the mass of the gas inside the rocket that's going to eventually be ejected is m sub g, and the mass of the rocket that's going to end up being deflected is actually 3180 minus the mass of the gas. We don't know how much gas is going to be ejected. They told us that it's going to be ejected at a certain speed. I believe they told us that the velocity of the gas is going to come out at 1750 meters per second. So when it fires the gas this way, it's going to cause this to move this way. But remember, the whole system is moving this way to begin with. It's going to continue to move that way. Newton's first law says it's going to continue to move that way, which means as it fires this gas out, it's going to move like this, because it still has this momentum and it acquires new momentum. So that's going to be moving off like this. Now I'm going to go ahead and draw and this would then be moving off like this. And when we consider both of these two separate objects now, and we add their momentums together, what we should end up getting is the exact same momentum that we started with. So I'm going to go ahead and start to draw some vectors here. I'm going to bring this one here represents the new momentum of the rocket, and this vector represents the new momentum of the gas. Now, again, the gas is being discharged. It's going to go like that. The rocket's going to end up moving like this. Because P initial is equal to P final, this vector represents the initial momentum of the rocket and the gas inside moving in this direction with that much momentum. Afterwards, what I have is the mass of the rocket here and the velocity of the rocket that I don't know yet. I don't really know what that value is, but I do know that its momentum plus the momentum of the gas must equal what we started with. Now let's go ahead and throw some additional things on here. The initial momentum, I'm just going to go ahead and say that the initial momentum actually has a magnitude of 365,700 kilogram meters per second. That's P sub I. That's the original momentum of the system. The final momentum is going to consist of two things that we don't know. I'm going to go ahead and put this one here to represent the momentum of the rocket after the gases has been discharged. It's moving off at an angle of 35 degrees. I should mention that here. So it's now 35 degrees from its original direction. I don't know the mass of that rocket because I don't know the mass of the gas, but I do know whatever gas is discharged, the rocket is going to have the remaining mass. So I'm going to go ahead and let's see, I think we can also call this value here. Actually, you know what I'm going to do is I'm going to go ahead and think of this gas vector, the momentum vector for that gas, to be composed of two components, and they would add together to produce the new momentum of the gas. This right here represents the amount of gas that was moving at 115 meters per second. So this right here is actually the This is actually the mass of the gas that's being ejected, moving at 115 meters per second, is actually what this vector represents. It's really a portion of the original momentum. I just don't know how much gas we're going to be ejected, but I'm going to go ahead and put it right there. Now I also have, let's see, I also have the black vector, which represents the new momentum of the rocket. I'm going to go ahead and put those, break those into its two components like that as well. And again, this thing right here, I'm going to go ahead and move this over here a little bit because I'm interested in these components of that vector. So let's see, this would be, this is the mass of the rocket times 115 meters per second. Again, these two, that one and that one represents the original momentum. I'm just treating it like two separate objects. So I'm just going to place them over here. This is actually MR, the mass of the rocket without the fuel that's being burnt, times 115, and this is mass of the gas. Now, what's also very useful here is that when I look at this component, this right here is actually the mass of the gas that's being ejected. It's actually the mass of the gas that's being ejected times the velocity of the gas, and I know that. So this right here represents the change in momentum that the gas experienced. Whatever gas mass that is, and it's being discharged at 1750 meters per second. Now that's not its actual speed, that's just its horizontal component of its speed. It still has 115 meters per second this way. So it's this is not drawn to scale. It's going to end up having a very large velocity this way and only a little bit of velocity this way. Of course, these are momentum vectors, and you know, so we'll get into that kind of stuff later. It gets a little bit confusing with momentum versus velocity, but needless to say, this is pretty important. Now down here, what I see is that this has to be the exact same momentum as that. So whatever this is, whatever that is here, this has to acquire the exact same change in momentum that the gas acquires. So these must be equal to each other. I'm going to go ahead and say that this then is also the mass of the gas, which is what I'm looking for, multiplied by 1750 meters per second. So this here represents the change in momentum that the rocket experiences to the right. This represents the change in momentum that the gas experienced to the left. Now, because I'm looking for the mass of the gas, I'm going to go ahead and look at this angle here. That's 55 degrees. And I'm just going to go ahead and set up a use some trigonometry to solve for the mass of the gas. And again, I'm doing that because I know this particular angle. I want it to be 55 degrees from the horizontal or 35 from the vertical. So I'm just going to go ahead and set this ratio up, or set up the tangent rather, to say the tangent of 55 is just a ratio of the opposite side, the mass of the rocket. And again, that mass of the rocket is the mass minus the gas down here. So it's whatever was left over here. It's this portion. Okay, so that mass of the rocket is actually this. And then I'm going to be dividing that by the mass of the gas, which is something I'm looking for, multiplied by 1750 meters per second. And when I go through and solve this, in order for me to solve this, I have two variables here. I'm going to go ahead and replace the mass of the rocket with the 3180 minus m sub g, and that will eliminate m sub r from that equation. And then I can just go through, and now it's just a fair amount of algebra to get to that mass of the gas. But it would look something like this: 3180 minus the mass of the gas multiplied by 115, and then I'm dividing that whole thing by the mass of that gas times 1750. And now I'm going to have to do some multiplying here. I'm going to multiply both sides by mg 1750. That would, and this is, you probably don't need to watch this if you don't want to, but I'm going to go ahead and put this here to get the equation set up so that it's a little bit easier to solve. And you can see maybe how we're going to solve it. Is equal to, I'm going to actually distribute this side, 3180 multiplied by 115, and then I'm going to go ahead and say that's minus mg times 115. That makes it a little bit easier for you to see. I'm going to go ahead and add this to both sides. I'm going to bring that over to this way, pull out an mg, and I'll get an expression for mg that will equal, when I plug everything in here, and I'll let you do the math there, it will equal 140 kilograms. Again, if you don't take into account the fact that the rocket itself is losing mass as it discharges the fuel, you're going to get 146 kilograms more than likely if you don't take that into account. And so it's a little bit tricky, but that's why we thought we'd record it. Hope that helped. Go Bucks.